The single sideband modulation overcomes the main drawbacks of the conventional amplitude modulation and the double sideband modulation. In this video, we will mention the main advantages of the single sideband modulation, but we will also discuss about the main drawback of this modulation, that is a drawback in terms of implementation. And we will introduce the vestigial sideband modulation as an alternative to overcome this drawback. The main advantages of the single sideband modulations are spectral efficiency and power efficiency. Spectral efficiency because the bandwidth of the modulated signal is equal to the bandwidth of the information signal that we are transmitting, the bandwidth of the modulating signal m of t. And power efficiency because all the power in the modulated signal is related with the modulation of the information. We are not transmitting a carrier in parallel that is not transporting information. These are the main advantages, but the single sideband modulation has a very important drawback in terms of implementation, because with the implementation using direct filtering, we need ideal filters to remove one of the sidebands. And in the implementation with a Hartley modulator, it is necessary to implement a Hilbert transformer, and the frequency response of a Hilbert transformer is also an ideal response that cannot be implemented without error. Here we illustrate these drawbacks with a graphical example. This is the frequency response of a modulating signal. This is the frequency response of the double sideband with double amplitude that is used in the direct filtering option. Here we have the two sidebands, and then some ideal filters are used to remove one of the sidebands, to remove the lower sideband in the upper sideband option, and to remove the upper sideband for the lower sideband option. Theoretically, everything works nice, but in practice, it is necessary to implement these filters, and it is not possible to implement a filter that instantaneously varies from 0 to 1 at a specific frequency, in this case omega c, or that varies from 1 to 0 at this frequency, at omega c. It's not possible to implement filters with this instantaneous transition from 0 to 1 or from 1 to 0. It is only possible to implement filters with a smooth transition about omega c. If this type of filters is used, there is a vestige of the sideband that was previously removed, this vestige here or this vestige here, and there is a distortion of the sideband that was previously transmitted without distortion, because now we don't have an instantaneous transition from 0 to 1 or from 1 to 0. The vestigial sideband modulation proposes to generate the modulated signal by means of direct filtering, like in the single sideband modulation, but replacing the ideal filters with implementable filters. These filters are called the vestigial sideband filters, and these filters must meet certain conditions. Now we are going to analyze these conditions graphically in the frequency domain. Here we have an example for the upper sideband variant. Here we have the frequency response of the double sideband modulated signal with double amplitude, and here we have the frequency response of an implementable filter, with a smooth transition from 0 to 1 around omega c. Therefore, it's possible to implement this filter. We really don't care too much about what happens out of the frequency band of the double sideband above W plus the bandwidth of the modulating signal, because here we don't have spectral components. Now, if we apply this filter to this signal, the filtered signal will have a shape like this one. We have a vestige of the lower sideband, and we have also a distortion in the upper sideband, because here in this part the filter is not one instantaneously. If this signal is transmitted, at the receiver we'll have a coherent receiver, a product with a cosine and then a low-pass filter. The product with the cosine will produce two replicas of this spectrum shifted to minus omega c and to plus omega c, each replica with half of the amplitude that we have here. We'll have the replica shifted to minus omega c, this term here. We will have the replica shifted to plus omega c, this term here, and this is what we have after the product with the cosine. Then the low-pass filter will remove these components, and here in baseband, maybe it is possible to recover the Fourier transform of the modulating signal. This depends on how these two terms are adding. If now we focus on this part, it is evident that to recover the spectrum of the modulating signal, the part that is missed here, that corresponds to this part in the upper sideband, must compensate with the part that is in excess, here the vestige that we have here in the lower sideband. This is equivalent to say that this part must be symmetric with this part. And this means that the frequency response of the filter around the carrier frequency must have an odd symmetry to guarantee that this lag here is compensated with this excess here. If now we look only for the frequency responses of the filter, this is the example that we have seen for the upper sideband example, but here we have an equivalent filter for the lower sideband case. It is evident that the shifted replicas of the frequency response of this filter move to baseband must add up to an ideal response in the frequency range given by the bandwidth of the modulating signal. Only in this case, the received signal will be an exact replica of the modulating signal under ideal transmission, without noise and without linear distortion introduced by the channel.